When a 2,000-ton cargo ship needs to stop in the middle of the ocean, it drops an anchor. That anchor weighs approximately 13 tons. The chain attached to it weighs 20 kilograms per meter. And when that anchor is released, it falls through 300 meters of water at terminal velocity, approximately 4 meters per second, dragging 6,000 kilograms of chain behind it. When it hits the seabed, the impact force is equivalent to dropping a fully loaded delivery truck from a 3-story building. And then something happens that almost nobody understands. The anchor does not dig straight down into the seabed like a spike. It does not immediately grip the ocean floor and hold the ship in place. And the chain does not go vertical from the ship down to the anchor. What actually happens is far more complex and far more brilliant than the simple image most people have of an anchor just hooking onto the bottom. The anchor falls, it tumbles, it lands on its side, the chain piles up in a heap on the seabed, and then as the ship drifts backward with wind and current, the chain gradually pulls tight and the anchor begins to drag, not because it's failing, not because it's too light, but because dragging is exactly what it's designed to do. And the physics of what happens during that drag, how the anchor rotates and how it buries itself, how the chain geometry creates a horizontal pull that multiplies holding force by a factor of 10, is one of the most elegant mechanical systems ever designed by humans. Today we're going to watch what happens from the moment the anchor leaves the ship, the moment it's holding 20,000 tons against a storm, every single second of the fall, every meter of chain, every phase of the grip. By the end, you'll never see a ship at anchor the same way again. Here's what makes this genuinely strange. If you ask most people how a ship anchor works, they'll describe something like a giant hook that digs into the ocean floor and holds the ship in place by sheer weight and grip. That description is partially correct, but it misses the actual mechanism that creates holding power. A ship anchor does not work like a car's parking brake where friction alone stops movement. It does not work like a tense take where you drive something deep into the ground and rely on penetration depth. A ship anchor works by burying itself horizontally, not vertically, using the weight and geometry of the chain to create a pulling angle that forces the anchor to dig deeper the harder you pull on it. It's a self-tightening system. The more force applied, the deeper it buries. The deeper it buries, the more resistance it creates, and the entire process from the moment the anchor leaves the ship to the moment it's fully set follows a sequence. That's the same whether you're anchoring a 200-ton fishing boat or a 200-ton container ship. We're going to walk through that sequence step by step. But first you need to understand what the anchor actually looks like, because the design you're picturing is probably wrong. When most people picture a ship anchor, they imagine the classic Admiralty anchor, the one with a long vertical shaft, a horizontal crossbar at the bottom called the stock, and 2 curved arms called flukes that dig into the seabed. That design is over 2,000 years old. It works, but it has a fatal flaw for modern ships. It doesn't store efficiently. The horizontal stock sticks out perpendicular to the shaft, which means the anchor can't be pulled flush against the ship's hull. It requires a complex handling system to stow and deploy. So in the late 1800s, engineers developed the stockless anchor, also called the patent anchor, and it's what nearly every large commercial ship uses today. Here's what it looks like. The anchor has a central shank, a long vertical shaft that connects to the anchor chain at the top via a shackle. At the bottom of the shank is a pivot point called the crown. 2 large curved flukes are attached to the crown and can rotate on a pin. The key feature: the flukes can pivot approximately 45 degrees from the centerline of the shank. This pivot is what allows the anchor to bury itself. When the anchor is being stored against the ship's hull, the flukes are rotated backward, parallel to the shank, so the entire anchor presents a flat profile. When it's dropped and hits the seabed, the flukes are free to rotate forward into digging position soon as the chain starts pulling. Let me give you the scale we're talking about. A typical stockless anchor for a 2,000-ton cargo ship. Weight 12 to 15 tons. Shank length 4.5 meters. Fluke span 3.5 meters across. Fluke surface area approximately 4 square meters per fluke. That's the size of a small car made of solid cast steel. And when this object is released from the ship and begins falling through 300 meters of water, the shape and weight distribution determine exactly how it falls, which brings us to the moment of release, when the anchor operator on the ship's bridge gives the command to drop anchor. The windlass brake is released. The anchor, which has been hanging just below the hawsepipe at the ship's bow, is suddenly free. Gravity takes over immediately. The anchor weighs 13 tons. It's denser than water. It begins falling at an acceleration of 9.8 meters per second squared minus the drag resistance of the water. Within seconds it reaches terminal velocity approximately 4 meters per second. At that speed, falling through 300 meters of water takes roughly 75 seconds. But the anchor is not falling alone. Behind it, still attached via the shackle at the top of the shank, is the anchor chain. This chain is not light. Each link is forged from steel bar stock approximately 60 to 80 millimeters in diameter. Each meter of chain weighs about 20 kilograms. The ship is deploying 300 meters of chain. That's 6,000 kilograms of chain following the anchor down. Here's what happens during the fall. For the first few seconds, the anchor falls freely. The chain is still being pulled from the chain locker inside the ship, feeding through the hawsepipe at increasing speed. The windlass, the massive winch that controls the chain, is spinning freely under brake control to prevent the chain from running out too fast and piling up. As the anchor falls, it does not fall straight down like a torpedo, because the flukes are pivoting freely on the crown pin, and because water resistance acts unevenly on the asymmetric shape, the anchor tumbles. It rotates slowly end over end as it descends. The shank may point downward for a few seconds, then tilt horizontal, then flip again. The flukes trail behind, creating drag. This tumbling is actually beneficial. It prevents the anchor from spearing point first into the seabed like a javelin, which would cause it to bury vertically and fail to develop horizontal holding power. At roughly 60 to 70 seconds into the fall, the anchor slows. The water at 300 meters depth is colder and slightly denser. Drag increases. The anchor's descent rate drops slightly. Then impact. The anchor hits the seabed, and immediately the chain behind it begins arriving. When the anchor hits the seabed at 300 meters depth, it lands on its side. The shank is lying horizontal. One fluke is touching the bottom. The other is pointing upward. The anchor is not dug in. It's just sitting there, 13 tons of steel, resting on mud or sand or rock, and then the chain starts arriving. Remember, the chain was falling behind the anchor during the entire 75-second descent. Even though the windlass operator has been controlling the deployment speed with the brake, there are still tens of meters of chain in free fall behind the anchor when it hits bottom. That chain doesn't stop falling just because the anchor has landed. It keeps coming. Link after link piles onto the seabed around the anchor. The chain doesn't pull tight immediately. It forms a heap on the seafloor in the immediate area around where the anchor landed. This heap is not a problem. It's part of the design. Here's why. If the chain pulled tight immediately, if it went straight from the ship down to the anchor in a vertical line, the pulling force on the anchor would be vertical or near vertical. A vertical pull on a stockless anchor does nothing. The flukes can't dig in if you're pulling upward on the shank. You'd just be trying to lift the anchor off the bottom. What you need is a horizontal pull, a force vector parallel to the seabed, so that when the chain pulls on the anchor, it pulls the shank horizontally, which causes the flukes to rotate downward and dig into the seabed. The way you create a horizontal pull from a ship floating 300 meters above the seabed is by deploying more chain than the water depth, a lot more. This is called the scope ratio. The scope ratio is defined as length of chain deployed divided by water depth. For a ship anchored in 300 meters of water, scope 321 equals 900 meters of chain deployed. Scope 521 equals 1,500 meters of chain deployed. Scope 721 equals 2,100 meters of chain deployed. The higher the scope, the more horizontal the pull on the anchor. Here's why. When you deploy significantly more chain than the water depth, the chain doesn't form a straight line from ship to anchor. It forms a catenary curve. The natural curve a heavy flexible cable forms when suspended between 2 points under its own weight. Imagine a suspension bridge cable. Same principle. The catenary curve of the anchor chain means at the ship end the chain angles steeply downward from the hawsepipe. In the middle section, the chain curves gently. At the seabed, the chain is lying nearly horizontal for the last 50 to 100 meters before reaching the anchor. That horizontal section is critical. When the chain pulls on the anchor's shackle, the pulling force is almost perfectly parallel to the seabed. This horizontal force is what causes the anchor to drag forward slightly. And during that drag, the flukes rotate downward and bite into the seafloor. Let me give you the angles. At scope 3:1, the chain angle at the anchor is approximately 18 to 20 degrees above horizontal. At scope 5:1, the angle drops to about 10 to 12 degrees. At scope 7:1, the angle is less than 8 degrees. Nearly horizontal. The lower the angle, the better the anchor sets. Industry standard for normal conditions, scope 5:1 to 7:1. For storm conditions or poor holding seabed, scope 10:1 or more. So for our 300 meter anchorage, the ship is deploying 1,500 to 2,100 meters of chain. up to 7 times the water depth, just to create the right geometry. And once that chain is deployed, the ship stops feeding out chain, the windlass brake is set. The anchor is technically down, but it's not holding yet. Now comes the critical phase, setting the anchor. After the anchor is on the seabed and the chain is deployed at proper scope, the ship is not yet anchored in the way most people imagine. The ship is still free to drift, wind and current and waves push against the hull. The ship begins moving backward away from the anchor's position on the seabed. As the ship drifts, the chain gradually pulls tighter. The catenary curve in the chain starts to flatten. The slack is taken up, and eventually the horizontal section of chain on the seabed begins pulling on the anchor's shackle. The anchor, still lying on its side, begins to drag across the seabed. This is not a failure. This is the designed behavior. As the anchor drags forward under the pull of the chain, the geometry of the stockless anchor forces a specific sequence. Phase 1, initial drag 0 to 2 meters. The anchor slides along the seabed on 1 fluke. The crown bottom pivot point is in contact with the ground. The shank is tilted slightly upward. Phase 2, fluke rotation 2 to 5 meters. As the chain continues pulling horizontally on the shackle top of the shank, the pulling force creates a rotational moment around the crown. The shank is pulled forward and downward. This forces the flukes, which are pivoting freely on the crown pin, to rotate downward. The fluke that was pointing upward starts digging into the seabed. Phase 3, penetration 5 to 15 meters. The fluke digs deeper with each meter of drag. The surface area of the fluke, approximately 4 square meters, acts like a plow blade. It cuts into the seabed, creating resistance. As resistance increases, the anchor drags more slowly. But the pulling force from the ship doesn't stop. It continues pulling the shank forward and downward. Phase for full burial 15 plus meters. Eventually the fluke is fully buried beneath the seabed surface. The shank may also be partially buried. The anchor has rotated from lying on its side to a position where the shank is angled downward at 30 to 45 degrees, and the buried fluke is acting as a massive subsurface plate resisting horizontal movement. At this point, the anchor is set. The ship stops drifting. The chain is bar tight. The anchor is holding. But here's the incredible part. The anchor is not holding the ship in place through its 13-ton weight. It's holding through mechanical advantage created by the buried fluke geometry. A 13-ton stockless anchor, properly set in good holding ground, can develop a holding power of 132-200 tons. That's a 10 to 15 times multiplication of the anchor's own weight. How? The holding power comes from the resistance of the seabed material against the buried fluke. When the fluke is buried and the chain pulls horizontally on the anchor, the pulling force tries to drag the fluke through the seabed material. Whether mud or sand or clay resists this movement through friction between the fluke surface and the surrounding soil. Passive earth pressure, the resistance of soil being compressed in front of the fluke as it tries to move. Suction in cohesive seabeds like clay, where the fluke creates a partial vacuum as it tries to pull free. In sandy seabed, a fully buried anchor fluke creates resistance, equivalent to moving a plate 4 meters wide and 1 meter tall through compacted sand. The force required is enormous. In soft mud, the holding power is lower. The mud doesn't compress as effectively. But even in poor holding ground, a 13-ton anchor can develop 50 to 80 tons of holding force. Now compare that to the forces acting on the ship. A 2,000-ton ship anchored in moderate wind, 20 knots and 1 meter waves, experiences a total environmental load. The combined force of wind pushing on the hull and superstructure plus wave action of approximately 10 to 15 tons of horizontal force. The anchor is holding 130 tons. The environment is pushing with 15 tons. The anchor is over-designated by a factor of 8 to 10. This safety margin exists because conditions change. In a storm, the environmental load can increase dramatically. Wind force increases with the square of wind speed. 40-knot wind equals 4 times the force of 20-knot wind. Wave impact creates dynamic shock loads that can momentarily spike to 50 to 100 tons. In severe storm conditions, 50-knot winds and 4-meter waves. The total load on the anchor system can reach 80 to 120 tons. The anchor is still holding, barely. But if the seabed is poor soft mud or loose sand or rock where the flukes can't penetrate, the holding power drops. And when holding power drops below the environmental load, the anchor starts dragging again. When a ship's anchor drags uncontrollably, it's called dragging anchor, and it's one of the most dangerous situations a ship at anchor can face. Here's what happens. The anchor is set and holding, a storm moves in, wind and wave loads increase beyond the anchor's holding power, the anchor breaks free from its buried position and begins dragging across the seabed. The ship starts drifting slowly at first, maybe 0.1 to 0.5 knots. The crew may not notice immediately, especially at night or in poor visibility, but the ship is moving. And if there are other ships anchored nearby or if there's a coastline downwind, the drifting ship is now on a collision course. The most common causes of anchor dragging: 1. Insufficient scope. If the crew deployed scope 3-1 instead of 5-1, the chain angle at the anchor is too steep, the anchor never set properly. When load increases, it pulls free immediately. 2. Poor holding ground. Rocky seabed or hard clay or areas with thick weed cover prevent the flukes from penetrating. The anchor skates across the surface without burying. 3. Overload in extreme weather. Even a properly set anchor can fail if the storm exceeds design conditions. A 13-ton anchor cannot hold a ship in a category for hurricane. At some point, the environmental load exceeds holding power and the anchor pulls free. 4. Chain failure. The anchor chain itself has a breaking strength, typically 200 to 400 tons for large commercial ships. If shock loads during a storm exceed this, the chain can part break. The ship loses the anchor entirely and is now adrift. When the crew realizes the anchor is dragging, they have limited options. Deploy more chain. Increasing scope improves holding, but only if the anchor ray sets. Start engines and motor into the wind using propulsion to reduce load on the anchor. Drop the second anchor. Most ships carry 2 anchors. Deploying both increases total holding power. Weigh anchor and move to safer anchor. If conditions allow, retrieve the anchor and reposition. The decision is made by the captain based on sea room distance to hazards, weather forecast and ship's condition, and sometimes the decision is made too late. In 2018, Typhoon Mangkhut hit Hong Kong while dozens of ships were at anchor in the harbor. Wind gusts exceeded 100 knots. Multiple ships dragged anchor and collided. Several ran aground. The anchors properly deployed in normal conditions simply could not hold against typhoon force winds. The anchor is a brilliant mechanical system, but it has limits, and when those limits are exceeded, 13 tons of steel buried 2 meters under the seabed is not enough to stop 20,000 tons of ship being pushed by the wind. The next time you see a ship sitting peacefully at anchor in a harbor, understand what's actually happening beneath the surface. 300 meters below the hull, there's a 13-ton piece of steel buried in the seabed. It got there by falling for 75 seconds, tumbling through the water, landing on its side and then dragging 15 meters across the ocean floor until its flukes rotated downward and dug in. It's holding that ship in place not through weight but through geometry. A horizontal pull on a buried fluke creating 10 times its own weight and resistance. And every few hours the crew checks the ship's GPS position to make sure that anchor is still holding. Because if it's not, if the ship has moved even 50 meters from where it was, it means the anchor is dragging, and dragging means the system is failing. The anchor hasn't moved because it's heavy. It's moved because the forces acting on it exceeded the resistance the seabed could provide. And when that happens, the crew has minutes, 2 hours depending on sea room, to respond before the ship ends up somewhere. It was never meant to be. Anchoring looks simple. Drop anchor. Ship stops, but what actually happens in those 300 meters of water, the fall and the pile and the drag and the set, the multiplication of holding force through buried fluke geometry, is one of the oldest and most elegant mechanical systems humans ever designed. It's been working the same way for 150 years, and it will keep working the same way until we stop using ships. Because some problems have a solution so good you don't replace it, you just make it bigger. If this changed how you see ships, subscribe to Valnor. Next video: the world's biggest ships have no brakes at all.